Okay, so we talked about the idea of a vector space in sort of an abstract way. Now we're going to look at it concretely. So on the board, what you see is Rn is equal to the set. Remember, when you see those squiggly brackets around, that means a set. The set of all column vectors with n entries. Okay, so notice it goes from A1 to AN, such that all the AIs, the entries that is, belong to the field R. And also keep in mind, I said the set of all column vectors with n entries. Well, remember that a vector is just a matrix that has one row or one column, in our case, one column. Now, before looking at concrete examples of why Rn is a vector space, remember, we've talked a little bit about how we add vectors. And we know one thing is that to add two vectors, they have to be equal, right? So we can represent that like this. And all this means is that two vectors are equal if the entries are the same. Okay, so if we want to add vector A and vector B, this is how we would do it. So we would do A1 plus B1, A2 plus B2, and all the way down to AN plus BN. So we know about the addition of vectors. We also know about multiplication by a scalar. So alpha A equals, and again, alpha A1, alpha A2, we can go all the way to alpha AN. Remember here that the scalars come from R, the R field. So think about it a little bit, because now we have some structure, we have now some object that can be multiplied and added, and that is what makes this a vector space, Rn that is. So we can write it out in these parentheses. We can do Rn, comma, addition. So we can do addition of vectors, and then comma, and we can do the dot, which is multiplication by scalar. And this is our structure. And again, keep in mind that the elements for the scalar or alpha come from the R field. They could come from the C field, let's say, the complex number field, but in this case, they come from R. And remember that part of the definition of a vector space in the previous video was that a vector space is said to be over a field. So in this case, it's over R. Now, the final thing is, what makes Rn a vector space are 10 properties. And said in another way, n tuples satisfy 10 properties. And I'm going to show you two of those 10 on the board. The first one is that if we take vector A and vector B, which belong to Rn, it implies that if we add vector A and vector B, their sum is a vector that belongs to Rn. So it means that if we add two vectors, A and B in this case, it stays in the same set or the same world. So that's very cool. The second one is if we have a vector A that belongs in Rn, and we have a scalar that belongs in R, so not Rn, but R, the field R, this implies that if we take a scalar and we multiply it by a vector, that vector still lives in Rn. It's still in the same set or the same world. And remember that all of these 10 properties all relate back to the addition of vectors and the multiplication by a scalar.